Welcome to Module 6, Lesson 1, The Logic of Experimentation and Causal Inference. I'm excited to dive into what many consider the most powerful tool we have in research, experimental design. By the end of our time together, you'll understand 3 critical concepts. First, you'll be able to explain the fundamental logic behind experimentation. Second, you'll analyze how experimental designs actually establish causal relationships, not just correlations, but true cause and effect. And third, you'll identify the 5 key elements that must be present for strong causal inference. Here's our focus today: understanding why experiments are called the gold standard for establishing causality. This isn't just academic jargon. There are specific, logical reasons why experiments provide the strongest evidence for cause and effect relationships. Think about this scenario. You notice that students who eat breakfast perform better on tests. Does breakfast cause better performance? Here's the problem. We observe relationships between variables all the time, but correlation doesn't equal causation. Multiple explanations are possible. Maybe students who eat breakfast also get more sleep, have more supportive families, or have better overall health habits. The direction of causation is also unclear. Perhaps students who are naturally more motivated both eat breakfast and study harder for tests. This brings us to the fundamental distinction between correlation and causation. Correlation means variables change together. There's a pattern of association, but we can't determine direction, and multiple explanations remain possible. Causation, however, means one variable actually influences another. There's a true cause-effect relationship with established directionality, but this requires specific evidence. Here's the key insight: correlation is necessary, but not sufficient for causation. You need correlation first, but that's just the starting point. So, how do experiments solve this problem? Through something called counterfactual reasoning. To prove that X causes Y, we need to know what would happen to Y if X didn't occur. But here's the fundamental problem. We can't observe the same person at the same time with and without the treatment. You can't give someone breakfast and not give them breakfast simultaneously. The experimental solution is brilliant in its simplicity. Compare equivalent groups. One group gets the treatment, one doesn't. If the groups are truly equivalent, then any differences we observe can be attributed to the treatment. But how do we create equivalent groups? This is where random assignment becomes crucial. Experiments require these essential components, and all must be present for strong causal inference. First, manipulation of independent variables. The researcher actively changes the presumed cause. You don't just observe who happens to eat breakfast. You actually assign people to eat breakfast or not. Second, control of extraneous variables. Eliminate alternative explanations. Maybe you control for sleep, motivation, and family support. Third, random assignment to conditions. This creates equivalent groups and is the heart of experimental logic. Fourth, observation of dependent variables. Measure the presumed effect, like test performance. Fifth, temporal precedence. The cause must precede the effect in time. Miss any of these 5 elements, and your causal claims become much weaker. Let's focus on what makes experiments so special: random assignment. This isn't the same as random selection, and this distinction is crucial. Random assignment means the researcher randomly places participants into groups. This accomplishes 4 critical things. It creates equivalent groups before treatment begins. It distributes both known and unknown confounders equally across groups. It enables causal inference, and it eliminates selection bias. Here's the important distinction. Random assignment enables causal inference. It lets you say X causes Y. Random selection enables generalization. It lets you apply your findings to a broader population. You can have one without the other. Think about it this way. If I randomly assign students to eat breakfast or skip breakfast, any differences in their test performance can be attributed to breakfast because the groups were equivalent before the manipulation. Random assignment controls for everything else: motivation, sleep, family support, natural ability, by distributing these factors equally across groups. This is why experiments are the gold standard for causal claims. They provide strong causal claims, the strongest evidence we have for cause and effect relationships. They're replicable because procedures are standardized. They control for alternative explanations through design. They provide precision in measuring specific effects, and they offer statistical power for detecting true effects. But experiments aren't always appropriate or possible. Ethical constraints mean we can't manipulate harmful variables. We can't randomly assign people to smoke cigarettes or live in poverty. Practical impossibility limits us. Some variables simply can't be manipulated. Artificiality concerns arise because laboratory settings may not reflect real-world conditions. Complex causation involving multiple interacting causes can be difficult to study experimentally. And long-term effects that take years to develop are challenging to capture in typical experimental timeframes. Before we wrap up, let's clarify 3 types of causal relationships you'll encounter. Direct causation is when X directly influences Y with no intervening variables, like flipping a light switch directly causes the light to turn on. Indirect causation involves a mediating pathway. X influences Z, which then influences Y. For example, exercise might improve mood by first improving sleep quality. Spurious relationships occur when a common cause creates the appearance of a relationship between X and Y, but there's no true causal connection. Remember our ice cream and drowning example. Both increase in summer because of temperature, but ice cream doesn't cause drowning. The manipulation component deserves special attention because it's what distinguishes experiments from other research designs. When we manipulate variables, we can vary presence versus absence, treatment versus no treatment, amount or intensity, low versus high dose, type or kind, method A versus method B, or timing, before versus during versus after. The key is that participants don't choose their condition. The researcher assigns them. This eliminates self-selection bias that could confound our results. Experimental logic applies across disciplines, though the specific applications vary. In psychology, we might study cognitive processes or behavior change. In medicine, we test treatment effectiveness through clinical trials. In education, we evaluate teaching methods and interventions. In marketing, we assess advertisement effectiveness and pricing strategies. The common thread is that all these fields use experimental logic adapted to their specific constraints and opportunities. A medical researcher faces different ethical considerations than an education researcher, but both follow the same fundamental experimental principles. Let's emphasize temporal precedence because students often overlook this crucial element. Causes must precede their effects in time. This seems obvious, but it's critical for establishing directionality and ruling out reverse causation. In practice, this means your manipulation occurs before you measure the outcome. you establish a clear timeline from cause to effect, and you consider appropriate time lags for effects to occur. Some effects are immediate, others take time to develop. Let's consolidate what we've learned. Experiments establish causation through systematic manipulation and control. All 5 key elements must be present for strong causal inference. Random assignment is the defining feature that separates true experiments from other designs. Experimental logic applies across disciplines with contextual adaptations, and understanding limitations helps us determine when experiments are appropriate and when other methods might be better suited. In our next lesson, we'll explore specific types of true experimental designs, post-test only designs, pre-test post-test designs, factorial designs, and more. We'll see how these principles we've discussed today get applied in practice. Here's what I want you to remember. Experiments aren't just one research method among many. They are specifically designed to answer causal questions. When you want to know if X truly causes Y, experimental design provides the most rigorous pathway to that answer. Ready to design your first experiment? Let's continue this journey in Lesson 2, where we'll put these principles into practice with specific experimental designs.